So, hello, good morning, everybody. So it's a long day today. We have two lectures this morning. One is new, this one, where we more highlight on medium and high temperature, because yesterday low temperature has been seen. For electricity generation. Okay, so if it is for electricity generation, we need also to deal with the storage. It's because you can't imagine to produce electricity only during the day and nothing during the night. So storage is a very important point. So I will deal with that this morning, medium and high temperature solar thermal for electricity generation. That will deal with solar collectors and also the association with storage and what is done. Then, in the second part of this morning, we will continue the story about PV design, and we finish the lecture about the PV design. We started yesterday about identification of all the components that are required for PV installation. And that will allow us to deal with some tutorials this afternoon. This afternoon, we will have one tutorial on hybrid photovoltaic thermal collector with phase change materials. So I will just start quickly to have an overview of what is a hybrid PVT, what has been done. And then we will see the evaluation of energy performance and exergy performance of such collector. In the second part, as it is mentioned on the program, it is mentioned to presentation of Polisson. But after thinking about that, it's only 1 hour. So I think there is no interest to show you. I will show you some tools. But there is no interest that me, by myself, I show you the tools in 1 hour. You will see nothing special. I prefer to make a tutorial on what is in the backside of these tools. So how they manage to exactly compute the position of the sun in the sky, how they manage to calculate some mask. I will show you some output of such a tool, and what they are dealing, and we make a small application on PV, autonomous PV design central. Okay, I think it will be all for the day. So I will start now by this. So don't hesitate if you have some question following my speech. We can stop. Okay, so if I have a highlight of the sun, if we compare the amount of energy that is available on Earth due to wind, biomass, hydro, geothermal, and energy coming from the sun, there is no comparison. The energy coming from the sun, it's much higher than all the other. And it could allow to reach 10,000 times world of energy consumption. The spectrum of the radiation is mainly centered in the visible in short wavelengths. It's very energetic on this. And so for PV, as I mentioned yesterday, we are using in the visible range of wavelengths around 1.2 micrometers for classical silicon components. Okay, see if yesterday it has also been dealt with my colleague about the solar constants. So solar constants out of atmosphere, he has demonstrated that it was 1,368 watt per square meters, and we assume that the radiation which is impacting the Earth is around 25% of this, and so around, in the mean, 342 watt per square meter. Okay, it's also consider, of course, the night in one side of the. So it's another way to present this time constant and this solar constant and what is impacting the Earth in mean. Just to remind you also, depending of the position where you are in Earth and of the position of the Sun, the radiation which is coming through the atmosphere, where depending on the inclination of the Sun and where you are on the planet, could cross one atmosphere. We say the air mass is 1.5, 2 atmosphere, if you are depending on the position. So for PV, as I mentioned previously, the tests are made with an equivalent of 1.5 atmosphere mass. That means that there is, of course, the path is very important because all along the atmosphere, it has also been shown by Pankaj yesterday that there is absorption of the radiation by some gases. Okay, so it is important to consider which is crossed. So I will go on this. What is arriving at the on Earth? So as I told, the mean is 342 watts per square meter. There is multi-phenomena that are implied. Only, but it's enough to warm up when there is greenhouse effect. 50% of this energy is absorbed by the surface of the Earth. Sorry. 20% is absorbed by the atmosphere, by the clouds. Around 20% is reflected by these clouds. So go back in the space. And 4% by the terrestrial surface. So it's more or less what happens. As it has been mentioned also, there is many different kind of radiation when you are on Earth. Some is coming directly, straight to you. So it's direct radiation. Some is reflected. Some is coming from the diffusion of the atmosphere. So what is the part which is reflected and coming from the diffusion of the atmosphere is said diffuse radiation when we consider the modeling at the scale of a building. It could be very important, this reflection part. It depends on the emissivity, reflectivity of the ground. Okay, so the albedo in some country where you have some snow, the part which is reflected could be very important. So now regarding the generation of electricity, there is 3 main sectors. So 2 main sectors for electricity, photovoltaic at the top, as we have seen yesterday, and thermal at high temperature. High temperature is considered to be over 300 degrees to 1000 degrees. When it is down, when it is lower, it's hard to use it as energy vector for generation of electricity, so we use it as domestic hot water or direct solar floor heating, things like this. So regarding the flat plate collector, the most simple, so at low temperature, very low temperature, is uncovered, so there is no glass. There is only an absorber and there is that means that there is no greenhouse effect. Okay, the radiation is collected by the absorber, but it's also a part is also emitted in infrared, not stopped by a glass. Okay, so this could be used for drying some fruits, eating some swimming pool, eating some big industrial container because the temperature is not so high. It could be useful. Then you have the covered flat plate collector. So it has been widely studied yesterday, but we had a glass, okay, between the absorber and the outside part that allow to keep, in terms of emission, the infrared emitted by the absorber of the solar collector. Vacuate tube. So when you are in a flat plate collector, you have a glass, you have air, you have absorber. So you can have some loss by convection between the absorber and the glass. Okay, the hot air coming from the absorber is going to the glass, and the glass exchange with external part. So you are losing a part of heat due to convection of the air between the glass and the absorber. When you evacuate this air, so there is no air, no gas, you erase this loss due to convection between air and absorber. Of course, it couldn't have a flat shape, because if you lay it like a flat shape, there will be an implosion of your glass. Okay, so it is in this way that there is a cylinder. Okay. So for low and medium temperature, the main application is for residential heating and domestic hot water. You can use it for industrial process that could require hot water. Typically for cleaning, there is a lot of industrial process like yogurt manufacture or milk. They need hot water to clean the big tank of food, and so it could be useful. It could also for drying, solar cooling. We will see some application of solar cooling with thermal energy. And so yes, the cost of course of evacuate tubes that allow to reach the higher level of temperature is higher. It's 1.5 or 2 times higher than the flat plate collector, which is quite common and standard. The performance of vacuum collector does not depend on wind or outside temperature due to the fact that there is no convection inside the collector to bring heat to the glass. Okay. It could be useful also for when you have a lot of energy need in terms of temperature. So typically it's hotel or hospital that need a lot of hot water and also to cool. So for the main problem of solar energy is it is a low density energy compared to the other. Of course, there is abundance of solar energy on Earth, but you can see the mean it is only 342 watt per square meter, the mean surface of the Earth. Whereas, so you need big surface, but even with big surface, you don't reach very high temperature. So if you want to reach high temperature, you are obliged to concentrate, okay? And so that's why if you want to have high temperature, you go on the concentration. You have to multiply on the same surface the equivalent of sun. Okay, it is this. So the geometric concentration factor is the ratio between reflector area. So you are, to concentrate, you are using mirror to focus on the same surface. Reflector area divided by the receiver area. Okay? So the higher the concentration factor, the higher the temperature is reached. Okay? Usually you have a huge reflector area and a small receiver area. Okay, if you have a lot of mirror focusing on this receiver, each mirror is the equivalent, if it is very clean, of one sun. Okay, so you multiply the sun on the same area. So there is multiple application, cooking, seawater desalination, more and more, because there is in some part crisis of fresh water. Pollutant treatment also, and especially microplastic in some water. Now there is some attempt to concentrate at very high temperature, or to use also UV treatment with the sun, photoprocess for this. Synthesis of nanomaterials, materials qualification, power generation, even, why not, cement generation. When we are speaking about concrete, the carbon footprint of concrete is very huge. And the main part of the carbon footprint of concrete is related to the cement, which require to be in furnace at a temperature over 1000 degrees. So you can reach such temperature with solar concentration. And there is some attempt about replacing furnace for the generation of cement by concentration. It has been shown yesterday, so you have what we call the dish, so two axis rotation. At the center part, I can here. So there is a parabol which is focusing on this engine, which is a Stirling engine that allow to generate electricity. So the Stirling engine is a dilatation and compression of air, like a piston, okay, that allow to generate electricity. You have one rotation axis, concentration factor is lower than 100, but it could be enough for generating electricity. Usually in the focal, so the tube that you see, it's not water, it's oil, to be able to go over 100 degrees. I didn't say that the concentration factor of a dish is around 10,000 focal, okay? So that means that in principle, on the small surface of the Stirling engine, you have 10,000 times the sun radiation, okay? If the dish is clean. If it's not clean, performance is decreasing very fast. Mirror has to be very clean. Then you have a mobile reflector, we call that heliostat, and with tower. So they reflect all the radiation on tower. So that means that we have to manage perfectly the inclination and the direction of the mirror to focus on this tower. Okay, there is two axes of rotation for the heliostat, and the tower is fixed. Okay, with one receiver. Concentration factor is around 3,000. Okay. Here you have the solar furnace. So you have, sorry, it's in French. At the bottom, abscisse is concentration factor. Okay, so you can reach 30,000 times solar energy in the same surface. Okay, so you can reach around 3,000 degrees, 4,000 degrees with such concentration. Okay, so it's hard to reach. I will show you one application. Then between 10,000 to 20,000, you need to be very careful on the management of the concentration. Typically, it could be with heliostat. You have big central with tower and concentration. And then lower, so between 2,000 and 10,000 concentration factor, it's quite easy. Okay. And so you can see the level of temperature that you can reach. You can reach over 4,000 degrees in one surface. So Gilles Flamand, which is the author of this, is very famous in the field of solar concentration because he was the head of, I will show you this nice laboratory in the Pyrenees, so in altitude. Why in altitude? Because the mass of atmosphere is lower. Okay, when you are very high in altitude, the AM is lower. And also you have less pollution, less particles in the atmosphere and so on. So you can reach very pure radiation on the surface. Okay, so it's with such a condition that they were able to reach over 4,000 degrees. On this is a lab in the Pyrenees. So it is the solar furnace of ODEO. You can see the lab is 6th floor, okay, and the parabole is the building, the whole building that will, so all the mirrors are concentrating solar energy here in one surface which is like this. Okay, so have you seen the number of mirrors? I didn't remember how much, but I think close to 20,000 mirrors. Okay, so here the question is that the south is behind the building. So it's strange. There's something missing. Yes, if you look, the parabole is not in the sun. It is in the north. So what is missing is that facing this, there is a big field of mirror. Okay, so the sun is here. Okay, the mirrors are here. So it is related to the fact that it is in the mountain. And the mirrors are all concentrating solar energy on this parabole. And this parabole is concentrating all the energy here. Okay? So that allow, because this is fixed, thanks to that, you allow to follow the sun and to reflect on the parabole. Of course, the building couldn't rotate like this so easily. So the principle, yes, it is this mirror follows the sun and injects the solar radiation on the parabole. This has been built, the first construction of this, the starting point of the construction of this was in 1960. So very, very long time ago. It almost disappeared because after, in the 1980s, France has developed nuclear energy a lot and stopped to work on solar energy. It was also almost all the mirrors were broken and things like that. And it is thanks to European project that this device restart in 2000, and the main research that were made with the European project is to work on the space application, aerospace application, and to work on some special materials, you know, for the space aircraft. When they are coming in the atmosphere, they need to be very well protected because there is some friction and the temperature of the materials are coming very high. And it is thanks for the research in space that this has been restarted, because they were at the beginning testing such materials for aircraft coming in the atmosphere, because they were able to reach high level of temperature, more than 4,000 degrees, and to test that, okay? And then after, for other applications, they have tested to make some cement, treatment of waste. They are doing a lot of things.
What maximum temperature they have reported?
They could reach around 4,600 degrees. The record, yes. So here you can see the wool. So they are fixing the sun and reflect on the parabol, which reflects here. Okay. Here, if you cross, you disappear. You can throw a wood and disappear. Okay, so it's very dangerous. Of course, you have to manage very well the heliostat and things.
Accident, like some bird is flying and then.
No, never. No. In a tower, in another place, there is a tower. So there is this system where they are also testing the management of the heliostat, and you see on the tower that they made a fault in the focus, and it has attacked the bottom of the tower. So yes, it's really impressive, and you see that it is in the mountain. You can reach 1 megawatt power. It started to be built in 1960 and finished in 1970. And so they study a lot of different materials, behavior, resistance under high temperature. If you go in this area, it is in southwest of France. It's very impressive to go and see that. It's really very, very nice. So the laboratory is Promesse, which is in Perpignan and also in ODIO. So if you have this summary, so concentrator with a tower, so and then after you have the system. So the system is to generate heat. So for example, now for the tower, the fluid is air. Okay, it's air. They are injecting the radiation in a kind of porous materials. At the backside of these porous materials, there is air, and those they take this air at high temperature, then heat exchanger with water of oil, and then go on storage. We'll see the storage, and generation. The same after, the principle is the same, as to generate some steam, and then to use turbine and to generate electricity. Okay, so whatever you have a Fresnel. So Fresnel, it's some mirrors that are reflecting in a horizontal focus. Okay, there is also some industrial application of that, and you have a cylindro-parabolic vector. Okay, so Fresnel is like this. It is you have one focal. And finally, you are building a kind of big parabol, okay, the level of ground to concentrate. So it's a lot of different mirrors that also manage to concentrate. So it's very interesting to work on the management of heliostat and of mirror. There is a very interesting mathematical computation to deal with that. And of course, the complexity is depending on the number of heliostat, especially also with the tower. It's very difficult to very well adjust each heliostat rays to focus on the tower. So the advantage, it's cheaper than the flat mirror, because it's flat mirror. It is flat mirror, so it's cheaper than parabol, okay? Because you are mimicking a kind of parabol with flat mirror, okay? It's lighter infrastructure. Disadvantage is optical performance is not so good as a parabol, around 30% less. But the main objective is to reach the sufficient high level of temperature, around at least 250 degrees, to generate steam and then electricity. Okay, when you have a summary of, you have to manage the heliostat, so the movement of the mirror. So you have also the receiver, that could be the tower, that could be another parabol as you see for the furnace. Then you are taking the hot fluid that could be oil or air, depending on the level of temperature. For such tower, it's generally not directly now steam, it's more air with high pressure, high temperature. Then there is heat exchanger with allow to generate steam, water steam. You have a turbine, okay, so steam power turbine, and injection on the grid. As I mentioned, for such a device, you are obliged to have thermal storage. Even if you are in a desert, where every day it's sunny, during the night you have no sun. So it's rare that a country don't need electricity also during the night. Okay, so most of time you have solar, you have thermal storage. Okay. So here it's also another way to show you operating principle. And so you have different also thermodynamic cycle that allow to recover after the steam, to recover part of heat when the steam is condensate, okay, and so on and so on. Of course, when the steam is in a closed loop, so you can recover a part of heat when the steam will be condensate as liquid water. Okay, some example in Spain here, Solar Central. There is 1,255 heliostat around the tower. Okay, the surface of heliostat, so the concentration factor surface is 120 divided by the reservoir. The reservoir is around 1 square meter, not so much. Okay, so avoid emission of CO2 and so on and so on. Here you have biggest also central. You can see you have you have 2 towers and 2 fields of heliostat. Okay, you have also a cylindro-parabolic collector, so it's a big solar high level of temperature, solar concentration. I think the biggest one at that time is in Israel. if I didn't remember. So some example so of different units. United Arab Emirates, a capacity of 700 megawatt. You have Morocco, United States, several ones. That one of the most recent is in United Arab Emirates with parabolic and solar power tower. Okay, so it's a mix between linear parabolic and tower. But I think the last two, yes, one of the last one is in Israel. Temperature range, so for parabolic you can reach between 300 degree to 400 degree. With tower you can reach 1000 degree, depend of the number of heliostat. Okay, most you have the field of heliostat is bigger, the more the concentration is and the level of temperature. So you can reach what are the strengths and challenge for such things. I don't know if you have some question on concentration. I just want to show you low temperature, solar low temperature generation of electricity. It's quite, I like this principle. It's not really developed, but I like this principle. But regarding the medium and high temperature, do you have some question about this concentration? It's okay. It's okay.
That plant, what you have shown, which was built in 1960s, now people are doing some research, right?
Yes, it's fully dedicated for research.
Now it is your personal. Now.
Now it's still a research lab from CNRS, and they keep on working on. Not really on concentration. Now they master the concentration since a long time. The management of heliostat also, they manage that, but they try to find new application for such furnace. What we can do, so they have developed some process to separate rare earths, for example, to lithium, to separate that, to treat some waste, to generate cement without consuming petrol and gas. So try to find new application. One of the applications that has been started to be studied, but is not really very efficient, is instead of the mirror, instead of the heliostat, why not putting some PV panels? Because it's glass, so in principle glass is also reflecting a part, but it's not really concluding. Okay, so there was a attempt to make hybrid PV concentrate solar using PV panels on the heliostat, because heliostat in principle is very well oriented. It's a kind of sun tracker finally. So if you put PV on the heliostat, it's good for the PV production, and so they were expecting to recover a part of the concentration, but of course you are losing a lot compared to a mirror. Okay.
You need more cooling.
Yes. Yes.
In the dish collector system, the temperature is very high, so for water.
Yes.
How the phase change, huge pressure, that will be managed?
For the steam generation, it's well managed, because yes, high pressure vapor is well managed since a long time for a classical burner. I didn't investigate on this topic very much, but it's a classical steam turbine that is used also for coal power generation. They burn some coal for generation of steam and then to use a turbine, but I don't really focus on that. Sorry. other question? So this application finally could be solar, low temperature generation of electricity. It is called solar pond. Okay, you have here a real development. So it's a large-scale energy collectors with water, with salt water. Okay, so you can use also this large surface as thermal storage, and it could generate a part of electricity due to the difference of salinization, difference of temperature. One is already working since 1988 in Bet Arava in Israel. His area, of course, is large. It's large area, 210,000 square meter, and it produces 5 megawatt. Okay, so it's funny because we said that with low temperature we can't produce electricity, and this system can. So it is based on a different zone. So it's a basin which is not deep. Okay, it's a large area of salt water, but not deep. So you have different of salinity profile, okay, and temperature profile, which are following the same in such a kind of components. So you have a upper convection zone, okay, because it's irradiate, okay, a zone which is non-convection zone, and at the bottom a lower convection zone. Okay, so you have convection down and at the top. So it could be considered as divided in 3 zones. So this solar pond is composed of salted water, okay, and the salt concentration is increasing with the depth. Of course, the density of water is higher, and from a very low value at the surface. Okay, because at the surface there is evaporation due to the sun radiation, so the concentration in salt is lower than at the bottom. Okay. So when you look at the physical phenomena, you have this, you have convection zone at the top, convection zone at the bottom, nothing in between. And so much of the sunlight reaches the bottom, okay. The bottom is heated, okay. It's reached the bottom because the depth is not high, okay, and the bottom is dark, so it will allow to heat the bottom. The salt water cannot rise because it is heavier. The density of salt water is heavier, so it couldn't move at the top, and thus the upper layer prevents convection current from forming. Okay, so there is 2 different zones. Without loss of heat, the bottom of the pond could reach 90 degrees. Okay. And so the description, I didn't focus too much on it, but the principle is that there is a transfer due to the salinity concentration, there is a transfer of electrons which are collected on this big surface and allow to generate a small amount of electricity. Compared to the surface, it is small amount of electricity, but if you are in the desert, for example, in Salt Lake, you can expect to have interesting production, even if the surface is large. It is the same for the tower of concentration with a large field of heliostat. Okay. So the temperature is nearly close to the ambient temperature at the top. The salt concentration is also near the clean water, okay? So like fresh water. Due to the contact between the top layer of this zone and the ambient, there is energy loss from convection and evaporation. So it seems to be obvious. The next zone, so in the middle, is non-convection zone. The salt concentration inside this zone is changed with the depth, so you can see it's not constant compared to the upper layer and the bottom layer. And the increasing of the depth from this interface results in the increasing of salt concentration. Okay, the last zone, so the lower concentration is most salt concentrate zone, and also the higher level of temperature, as I mentioned, because as it is not so, the depth is not so high, the radiation is going till the bottom. Okay, so it's a mix between thermosiphon and then there is yes, a recover part of electron due to the difference of salinity. So this kind of component have been started to be studied in 1948, and there is now some kind of application. We don't find too much information about that. We know that there is real application, so it could be interesting also to study that. I just discovered this kind with my students this year, because I give them some bibliography about solar application, and some have identified that I never saw that before. And I found it was interesting to share it with you, because finally it's a kind of solar low temperature generation of electricity. Okay. The efficiency is around 15 to 20%. So the pan efficiency is defined as the ratio between the quantity of heat extracted from the pan divided by the solar insolation of the pan area. The efficiency for electric energy is not very high. As I told you, you need very big surface, but for real application, it has been proved that you can reach some power. So it's 0.8 to 2%. And for a typical area in the Middle East, where the global radiation could be estimated at 2,200 kilowatt-hour per square meter per year, you can expect to generate electricity between 20 to 45 kilowatt-hour per square meter per year. And heat energy, it's a hybrid system that you also generate heat. Okay, so it could be interesting to focus. Disadvantage is that it's not working well at high latitude, and due to evaporation, of course, you need some water at a certain point. Okay, if you are in a desert, if you want this system to continue to operate, you have to inject some water. Otherwise, you will have a dry salt lake without water at the end. Okay, so did you know this kind of collector? No. I don't know if you have some question. I was thinking to add this.
Maintaining the salinity,
Yes.
gradient.
Yes, you.
Otherwise, no, it will be same concentration.
It's automatic due to the fact that at the upper level there is evaporation and low temperature, and due to the volumic mass, the more high level of concentration is at the bottom, which is also at the higher level of temperature. And so this the process is then operating like this. If the depth is not so high.
With time diffusion will take place.
Hmm?
With time diffusion will take place. And then you need to maintain some salinity maybe by
Yes, you need, yes.
Is there any ionization?
Yes?
Is there any ionization, because to produce electricity we have some positive and negative charges?
Yes, there is a real...
Here actually no, we use organic Rankine cycle. So here actually heat only we are using, and then electricity we are using organic Rankine cycle.
Yes.
Low temperature
Yes,
power
yes,
generation.
yes, low temperature.
So this is a real application that I have identified.
In India also we have.
Ah, you have?
Infuse.
Okay.
Infuse. They have in there. That they use for dairy application.
Okay, okay.
Gujarat.
I find that interesting, yes.
Gujarat.
Do you have question? I was thinking to have put the solar the storage also, but it will be in my lecture of tomorrow, I think. Sorry. We will see the thermal storage for sure. Do you have question, or maybe we can do a break now? It's okay, or is too early? Half an hour. I can maybe speak about the thermal storage, so if you want. Okay, I got to find it there. Storage. Ah, sorry. Sorry. Maybe what I suggest is to restart on PV design until the break and then continue on PV design. Okay? Because I didn't remember if it is tomorrow or after tomorrow that I will speak about thermal storage. Okay? Can we put the presentation of yesterday? It was day 1 and 2. Yes. Okay. Like this, we continue a bit on this and. So we are on this, and so we were on the connection of all the components. Okay. So to remind you, for a grid connected, you have the PV central, switch off of this PV central that allow to fireman to disconnect the PV central if there's a problem of fire. You have the inverter, and you have electrical meters. The more complicated is finally for autonomous design, where you had the battery, and we have seen that we have many ways to couple of the components depending of the needs, and so for the management of the charge and discharge and the connection to the battery. Okay. When you are connecting the modules, we have seen that we need to have the same modules per string, the same modules for the whole PV central also. It's dangerous if you combine some different branch of PV modules, because if you have any difference between operating conditions, we call that mismatch effect. You will induce not a very optimal production of the PV central. We have finished on the way to connect the inverter to your PV central. We have seen that the main advantage to have one inverter for the whole central is the price, but the other advantage are in favor of multiplying the inverter in order to avoid, if there's a problem on the PV central, to avoid to generate a mismatch effect and then a bad or a breakdown of the whole PV central. The inverter is very important, so it's an electronic device, okay, and is allowed to maintain a quite stable operating condition. So to maintain a quite stable operating condition is integrate in itself some capacity, okay? So to avoid all the fluctuation. That's why when I was speaking about yesterday the PV coupled to the battery, the main, an important device is to add some charge-discharge controller, but if you can also to integrate an inverter, MPP tracker, that allow to have a stabilization of the production in both directions, but so it's inducing the integration of battery, of capacity. So if there is capacity, it gives us an idea about the lifetime of such components. Do you have an idea of a lifetime of a capacity? And it is the weakest element in a PV central in terms of lifetime. It's like a battery, so finally it's around 8, 9, 10 years, okay? So lifetime is around, about 10 years, 8 years. So when you have a PV central, sometimes there is some economical agreement that, for example, somebody or a PV, energy provider can rent your roof. You say, I want to rent your roof. I will install the PV central. I will sell the electricity, and after 10 years, I will give it back to you. Okay. So you have to be caution if it is just before or just after the inverter collapse, okay? Because the cost, if you have one PV central with one big inverter, the price could be very expensive, okay? So it is the weakest, part of PV central. if you are in autonomy also, if you add some batteries, the weakest part will be the battery. The lifetime of the battery is around also the same range, okay, 8 to 10 years. So, how the maximum power tracking is operating? It's like by test dichotomy. You are starting. It's an electronic device. Okay, it's starting to fix tension, computes the power. Then he had a small discrepancy of tension, of voltage. Compute the new power. If the new power is lower, so that means that the maximum, the optimal value of the voltage is lower, so it's going down, so it's decreasing the voltage. See the power generation. If it's bigger, it's going down. Okay, it's like this. Of course, it is very fast, but also it is using the hill climbing method. Okay. So the algorithm is you are changing a bit the voltage. You look at the power. Okay. If the power is higher, so it's good. So you are keep on increasing the voltage until the power is not higher. And so you will find finally the maximum power. So it is this way that the maximum power is identified when the PV central is operating. Okay, so of course the quality of the inverter is to be able to compute, to identify this maximum power as soon as possible. So the rapidity to identify this maximum power is very important. Also, the inverter has to be selected in a consistent way compared to the power of the PV central. If the inverter is not well designed, so is over, for example, over estimated, over designed compared to the power. Of course, he will all the time find the maximum power, but the accuracy will not be so good if the inverter is too big compared to the power. Okay. And if the inverter is lower than the power of the central, when the power will be over the capacity of the inverter will disconnect. It will not be able to find the maximum power because it is under design compared to the global PV power. So it is very important to well design this and to adapt it to the power generated by the central. Here you have an effect of a shading effect. For example, here you have a PV central on a roof, and maybe in the afternoon, after 2 o'clock, the wall which is here is making shadow partially in some modules. Okay, not all the modules, or one module is fully under shadow, but just a part. You can see here the effect on the intensity, okay, if depending of the number of the cells that are on the shadow. So in yellow, if there is 20% of the cells of the module that are in a shadow, in blue 35%, and you see the impact on the power is huge. Okay, of course it's huge because it's a product. So it's very important also when you are designing the PV central to be aware and to compute the close mask and the far mask, so the mountain and also the building by itself or the surrounding buildings, because you can really impact. So you can have also the impact of the trees between winter and summer. In winter, if the trees have no leaf, it will have no impact. In summer, it could have big impact. You could have a chimney or ventilation system. So a chimney that could be narrow but high could induce all the day long, finally, shadow on the PV central when the sun is running. Okay. Some example of installation here in Munich. You have 3 inverters for a big central. So you have here the panels here. So of 1 megawatt, you have 3 inverters of 330 kilowatt ampere. So the series, for example, here you can have some unit power from 500 watt to 5 kilowatts. So it's small. As I told, the gain is the flexibility, easy maintenance, and of course you have also some disadvantage that you are losing each time you are converting, so you are losing a bit more also because you are multiplying the inverter. An example here also in Germany, for the same power, so 1 megawatt peak, you have 600 inverter of each 1.5 kilowatt hour. And so, as mentioned, if you have 1 inverter per module, the efficiency is a bit less, but after the feedback we have on this kind of installation, you are producing much more electricity within 1 year, because, as I mentioned, if one of the PV panels has a problem of operating, you will not destroy the wool production. Okay. So you have here an example in Amsterdam, in Holland. So it's a long motorway. It's to protect from the noise. So it's a wall, a PV wall, and a noise wall. So for a power of 216 kilowatt peak, you have 2,000 inverters. Okay. So it's a huge difference. Here, interesting solution is if you have multi-string, so you can have several inverters because you want to optimize the production all along the day. So, for example, you have a house with a roof with 4 different orientations. You can put at the east to start to produce the morning, at the south, and at the west. For a dwelling house, it's very expensive, but for some tower, it could be interesting to study or industrial application. It could be interesting to have 3 different maximum power tracking and inverter. As soon as you have different orientation, even if it is on the same system, as soon as you have different orientation, different local particularities that could induce a difference of operating, you have to distinguish the inverter. Otherwise, you will impact too much your production, and also it's not really good for the global inverter that will be connected to the grid. Okay, so this is, you are starting from the PV, the inverter, and to connect the PV panels and all this stuff, you have to use cables. You are obliged to use standard cable because there is big risk about this cable. The main of the current which is crossing this cable is continuous current, so you can have a high level of intensity, and if the cable are not very well designed, you can have some problem and fire problem on PV installation, for example. So of course you have to design the section of the wires that able you to transport this intensity. Okay, and so of course it depends of the Joule effect, so the resistance that will, and the Joule effect that will be induced due to the intensity. So the resistance of the cable is depending on the section, and so you have to design it in relation with the intensity which is going through. So there is some standards, okay. This cable also to have a specific envelope, okay. Specific because usually these installations are outside, or the cable are outside, so they are submitted to UV, okay, and the UV is very strong for attacking the polymer, so this cable has to have UV protection, especially because such PV central could have a lifetime around 20 to 25 years, okay? So 25 years outside submitted to UV could be very damaging. You have also to have secure connectors, okay, like this, in order also to, for the installer to be not confused between the plus and the minus when they connect the PV in between, and so to avoid also, of course, water infiltration or other thing like this, so to be fully protected. And yes, the contact resistance has to be very well studied in order to avoid most of the problem when you have seen maybe some problem of PV central on a roof with fire. It is because the cable were not very well designed, or the PV panels not plugged as it should have been. It's not related to the PV panels or other electronic components. It's connection and cables that have not been well designed. Okay. Then we start with the battery, and this afternoon we will need that. So a battery, generally for capacity, the unit is coulomb, but we are using equivalents. It's like joule and kilowatt hour. Coulomb and ampere hour is the same kind of transformation. So for battery, we are using the unit of ampere hour. Okay. So when we said that battery has a capacity of 100 ampere hour, that means that it is able to provide 1 ampere during 100 hour, okay, or to be able to provide 10 ampere during 10 hours, or and so on and so on, okay. So you have some standards that, for example, the capacity 10 corresponds to discharge current of 10 hours, okay. For example, if you have a capacity of 100 ampere hour, that means that it will be 10 hours of discharge, 10 ampere, okay. So it is a convention which is used for the battery. One important thing, and after we can maybe make a break on it, it is the number of cycle, okay, and related to the number of cycle is the depth of discharge, okay. So we never discharge completely a battery, which it will, if we do each time 100% of discharge and recharge, the number of cycles will be limited, okay. The more you are going in the depth of the battery, the more you are limiting the number of cycles. Okay, it's quite simple, and it's not linear. Okay, so that means here it is extracted capacity. Okay, but it is the same. So if you are only using 20% of the battery, okay, in terms of discharge, you can have a large amount of cycle. If you are using 100% of the battery, so the depth of discharge is 100%, you see that you are limiting a lot your number of cycles. So when you will have to design it for the PV central, you have to make the choice. And of course, it has a huge economical impact. If you have a lot of money to invest at the beginning, okay, so you are quite comfortable on the design of the battery, and you can say, I will choose the depth of the discharge of 50%, for example. That means I will use it maximum at 50% of the capacity. That means that regarding the real need you have, you will double the size of the capacity. If you use only 50% of the capacity of the battery, regarding your real need, you will double the capacity. So that the price almost multiply by 2. If you have not too much money at the beginning for the investment, but you say that you know that every 3 or 4 years you have money in order to maintain the PV central, you can choose to go deeper in the use of the battery. That will reduce the investment cost. So you can say, okay, I will use my battery at 80%. Okay, but you know that you will reduce the number of cycles. So the lifetime finally. Okay, so you can say, okay, I have not so much money at the investment level, so I choose 80% of discharge, but I know that the lifetime, instead of being 9 years, will be, for example, 6 years or 5 years. Okay, so that in 5 years, for sure, I will have to change. Maybe not all the batteries, it's not, but some of the battery I will be obliged to change it. So it depends at the design step. If you have a lot of money for the investment and not after for the maintenance, or if you have not too much money at the investment, but you know that regularly you can inject money for maintenance. Okay, And the price of battery is a very important topic, because when you add battery, the price of a PV central is increasing a lot. Okay. But for sure, never design it for 100% of use. Don't forget that, because otherwise you will more than divide it by 2 the lifetime of your battery. After 2 or 3 years, they will be out. Okay. So we can make a break now and continue after. Thank you.
We'll be joining.